Hello, Flat Earth researchers, debaters and debunkers. We were all fooled once into believing intangible, indirect evidence leading us to believe that we live on the outside of a spinning globe, despite our tangible, physical reality, and really down to ignorance of the way we actually see the world. So I've often said that the geometry of perspective is the imaginary curve of the Earth. So I'm just going to try and very simply, as usual, illustrate and demonstrate that to some extent. So here we can see tangible and intangible. You can see that this might be some kind of view of, say, windmills, a row of windmills. We're looking side on at this view, and in that case we would have a tangible measurement. We would know the actual length or height of those windmills because we made them ourselves. So they would have a very tangible measurement. Of course, if we are just making an observation, then these are not really tangible, but the point is we already know, we have physical measurements. And this will be a familiar view of just looking at this row from a side-on or orthographic view. And as we can see, it's always level. The water and the horizon is always level. Now you could also assume that these are lights in the sky, or it could be one light in the sky that is making its way across the sky, and we're observing it at different intervals, different time intervals, if you like. We can imagine it like that. Okay. So what happens is in this view is we are the observer, and as I said, we know the tangible height, the measurements of these. Okay. But now what happens in this intangible view? What we have, of course, is these same lengths or windmills, if you like, or light posts, whatever, or even stars or the sun in the sky. And we know that if we are standing somewhere in the middle or at the end of this row, and then we're looking along that row, then this is the kind of effect we'll see. We'll see these posts appearing to get shorter and shorter in the distance. All right. And again, these might be measured. We might know that they are a certain height, but of course, as they go further away, they appear to be different height. Again, the surface is just level. Nothing changes there. So if you're fairly new, or even if you're an old hand at this, you'll have seen these claims that pylons appearing to curve down in the distance are Earth curve, whereas the horizon is completely flat. But what we have is this effect of perspective, because what we have is an observer's view. So obviously here we've got a row on the left and a row on the right, and we're in the middle of this row. So we know that, for example, if we were in this view here, and let's say these ones here are these on the right, and then we can see another row off to the left, we know that they would actually appear shorter. Okay, because they're further away, right? So even though these are the same height, they will appear shorter. This is really simple stuff. Anyone can just check this for themselves. This is just how our eyes work. So even though we might know that they are the same length, we've got tangible measurements, them being further away makes them appear shorter and lower. And of course, this is what is passed off as curvature on the surface of the Earth. Again, perspective is the imaginary curve. People will look at these and say, oh, that one in the distance and those ones in the distance have gone down a curve of water, which of course we never actually see. And we know instinctively that it is because of perspective. Okay. So just briefly, let's talk about tangible and intangible, just to clarify the difference here. I've been having, since my last video, about basically showing the moon coming overhead here from east to west. We've had people arguing for this heliocentric model, saying that you don't do anything to scale. You have to know the scale of the model. And so my question is, well, you need tangible measurements before you can talk about scale. Otherwise, if you're making some kind of scale model, you can put things wherever you like. So here is a this is really simple. Here is a scale model of a car. We know it's a car. It's it's got all these dimensions that we can scale up, and if we did it accurately, we would have a bigger version of this car, right? Or this model is made from, it's a scale model of a real tangible car that we can hold in our hands, or we can walk. If it's a large one, we can walk around it, we can touch it, we can physically measure it. We can measure the roof, and we can measure the angle down from the roof. We can measure the distance apart from the wheels and things like that. Everything can then be made to scale because you have a tangible measurement of the real thing in the first place. And this is where the heliocentric model is not science. Creating a scale model requires mathematics, but it's also proper science, because first of all you have to create the tangible object, you have to measure it in a tangible way, and then you can scale it down and create a scale model. But when it comes to the heliocentric model, or this idea that we're living on a globe spinning around at 1,000 miles an hour and orbiting the sun, none of these assumptions, which is what they are just assumptions, none of these assumptions are based in any fundamental tangible measurement. Unlike this scale model of a car, there is no tangible measurement of, for example, the size or the distance of the moon from the Earth, or even curvature on the Earth, like a curve you might see on this car here. There's no measure of that on the Earth. What we do have, though, is a conversion of our intangible perspective, the way we see the world, converted into this side-on view that assumes the Earth is curved, when really what it's done is taken the geometry, or you can use trigonometry, of perspective. All right, so just as a quick example of that, which we from grade school or whatever, okay, you know that if you wanted to measure the height of a building, say, yeah, you can just get to a certain distance away from the building and then measure measure an angle up to the top. And if we have 45 degrees, if we have an angle of 45 degrees up to the top of this tower, then we know that this length along here is equal to the height here. Okay. That turns out to be fairly accurate. There's this thing about 45 degrees being able to do that. But anything that is less or more than 45 degrees ends up being an intangible. This isn't really tangible, but it's a formula that works. So here we have some basic trigonometry. Okay. And so you could, if you like, apply that to one of these lights up here, if you like, and you could measure a 45-degree angle from your observation place. And so if you had a 45-degree angle, for example, let's just, do that, yeah, like that, 45 degrees here, you're standing here making the observation, then maybe you get the same distance as you do for the height. So, maybe if you actually do those measurements, you do end up with a sun or a moon or stars that are a few thousand miles away. Why not? There's nothing that we can do otherwise to measure. All we can do is make calculations and assumptions. Okay? So you understand the point, yeah? The further away you get, the smaller this is going to appear. So the angles will not then correlate to the actual size. You can't convert those angles into the actual size of the object. Yeah, let's just rub that off. Okay, makes sense. So again, with trigonometry and geometry, you're playing around with angles that are either 90 or 180 degrees, and you're finding somewhere in between those angles, yeah? But again, what we're doing is we are converting the angles that we see in perspective into a curve. So let's just try and illustrate that in a way that makes sense. You see, it's really, really fundamental to understand that this view is not the same as this view, is it? Yeah, they are starkly different. So what's going on? We have a change in this view, and this change in view can use geometry or trigonometry, if you like, to describe the effects of perspective. Okay, so the geometry of perspective is the imaginary curve. So it's really quite simple, because if you had, for example, an observer here, okay, this light here is going to be directly above their head, right? So, that's going to be your 90 degrees. Okay. So whenever we're doing these things like this, we're always talking about 90-degree angles like this. Okay, you've got your horizontal and you've got this upright, and of course you can go the other way. You've got another 90 degrees, and you've got another 90 degrees, and of course, so you end up with 180. These are the angles that you get. Yeah? Well, these are the angles that we're working with. All right? So in reality, or what you could say Euclidean geometry, the tangible way we measure reality, we have parallel lines. We have the surface here, the level surface, and if we just all of these, because they are the same height, they create a parallel line of the tops of these lights or windmills or whatever you want to call them. So in reality, the distance between these lights and the surface remains the same. It remains constant. Again, if this is a light that is traveling away from us, or we're traveling away from it, then it carries on at the same height above the surface. It's not curving. It maintains a parallel, level, truly level line. Okay, but of course, from the observer's perspective here, so sorry, maybe I should just add this. So then we have a right angle. We've got this vertical. Okay, let's put our observer down here. Again, just reiterating the scenario above. Okay, but we've got this vertical, and then the horizontal is it helps create the right angle. We also have the observer's line of sight, so we have another right angle here. Okay, so of course what happens is, as the observer looks this way, in the observer's eyes, this one is going to appear lower, and this one is going to appear lower, and this one is going to appear lower, just as we see here. We see this apparent declination. Again, we're talking about indirect evidence. This is something that we see occurring, but it's why would you assume that the Earth is curving when we know that this is what happens when we see through our eyes how perspective works? Okay, so from this, if we take this side-on view and we convert what we see here, the surface isn't doing anything. Well, it is, but we'll come to that. But what we see, if we look either way, is this declination. Okay, so again we have our right angles here from the observer's horizontal line of sight. Okay, so now what we have is, this is, you could call this, what do you call it, spherical excess, if you like, because now we've gone, this 90 degrees has gone, we've gone beyond, we've gone 90 degrees, and then this further down has gone down. So, we've got this kind of curvy effect. Yeah. Again, you can use trigonometry or geometry, but what you've got is this declination over distance due to the difference in angular size, which is what we're seeing here. So this declination of these lights is the declination of these lights in the sky. Well, what about the surface? Remember that all these observations are done with establishing the horizontal and the vertical. So you've basically got a horizontal perpendicular to plumb. Okay, that's fine, it doesn't matter. You can assume your line continues going down there to wherever you like. But it's not the surface that's curving, it's this that's curving. But what appears to happen to the surface is here is the observer's eye level. Okay, in this case we have the surface here. Again, this is why I'm talking about what, it's tangible. There's a tangible difference between the height of between the surface and the height of the observer, or the observer's eye level, if you like. Okay, yes, we can call the eye level the observer's height, and we can also talk about that horizontal line of sight as being that observer's eye level. So here we have a horizontal line of sight. So just as these things in the sky part of our view, the horizon is the division in our eyes between the surface and the sky. So what's actually happening, again, I'm illustrating what's happening in the eyes, not the physical reality, but what we see happening in our eyes is a surface that appears to rise to eye level. Yeah? Okay, so we've got declination here, and I suppose you could call this inclination if you wanted to. Yeah? And this is really just, this is how angular size works, right? People often, again, compartmentalize angular size to talk about the things in the view. But the whole view is getting compressed in angular size, isn't it? Everything, yeah? And again, what you'll notice here is all of these up to a certain point, depending on our height. The horizon will appear at a certain place depending on our height. It will always be our eye level, and it will indicate how high we are. But you'll have all these things going up to the horizon, and they will be below, if you like, or in front of the horizon. But then eventually you get to a point where things are so far away that they are just on the horizon, and eventually they just become part of the horizon. They are no longer visible. This line of lights or row of lights or windmills or whatever could go on for miles and miles and miles, and you would not see the ones that get too far away if you're only a short distance above the surface. If you gained height above the surface, then maybe your horizon would appear higher up, and you would see more of these on the surface. Yeah? But this is, detracting from the point. The curve is here. This is the curve of perspective. This is that translation. But so the geometry of perspective is converted into this imaginary curve. Yeah? Maybe this isn't very clear, But what you have from the observer's perspective on I'm going to try and do a flat surface here. All right, this is flat, okay. And what you have from the observer's perspective is something at 90 degrees, and then it's going to go down and down and down and down and down. And so it's going to go down and down and down and down and down on the other side. So what you have now is a dome of perspective. Yeah? Yeah? A dome of perspective. The surface didn't curve. What happened was you just basically had these differences in the angles of the apparent height. Now, so this could be, for example, this could be the North Star, if you like. Yeah? And you've got a dome either side. Or I could be standing here on the equator. Okay, here's me on the equator, and this is going as far as I can see north, and this is going as far as I can see south. Okay, so you have a hemisphere. The hemisphere of the globe is just a hemisphere of perspective. Now, again, keep in mind that the distance we can see across the surface is relatively short. Why? Because it's solid and it will appear to take up the lower half of our vision. So if we are low to the surface, I personally do not dispute the distance to the horizon. Let's be clear about that. If you're at a certain height, the distance that you can see to the horizon will be short or long. That is the horizon on the surface. But what we see, so for example, we might only ever be able to see to this point on the surface. Obviously need to make the guy a little bit shorter there. Okay. Dun, dun, dun. There's our guy on the surface. And this is the distance to the surface horizon. Yeah. Okay. But the distance that you can see something in the sky, obviously the higher up it is, the further we'll see it. So we'll, even beyond this point here, we'll still see things in the sky continue to decline. We don't see the surface, there's just a short distance across it. But the transparent sky allows you to see much further. But of course, another thing that happens in the sky is you've got things like clouds, yeah? And overall density and dust and water vapor that will eventually obscure our view. And again, due to angular size, this gap of air could be 100 miles high, but we wouldn't see anything. It would just become part of our horizon because of this angular size. Yeah, and that's it. That is it. Okay, navigation and all that stuff is based on looking at the stars. There has never, ever, ever, ever been a tangible measurement of curvature on the surface of the Earth. It's all, the entire heliocentric model is cobbled together with a bunch of assumptions, and simply by converting the perspective, the geometry of perspective, when we make observations of things in the sky, into a curve, an imaginary curve. Yeah, you can imagine this as a triangle if you like, okay, or a curve. Doesn't matter. But obviously, for the sake of the heliocentric model, then they would prefer to have a curve. All right? It's as simple as that. So again, just to reiterate, this is a scale model of a real tangible object. All right? But when you start talking about distances and assumed distances to stars or the sun, so here we've got a sun in the sky. Okay, let's put the sun up there. And, you know, maybe you have the moon. We could put the sun up here and the moon over here. Yeah? All right? They are both going to appear lower in the sky than they are physically. Okay, so they could be both at the same height, the same distance from the Earth. They do appear to be about the same size. And why not? Well, why not? Because you have this idea that we're going around the sun, and so you need to create a lot more space in the model, the scale model. But you don't have a scale, we don't have a tangible measurement. We do not have a tangible measurement to the sun or to the moon from the earth or between each of those bodies. We have nothing. All we have is lights in the sky. Yeah? No tangible measurements from which to create a proper scale model. So the only thing about the heliocentric model, the scientific concept that it is built upon, is simply being able to tell the time and make predictions. Of course, in the scientific method, if you have a theory and you make predictions, then your theory would appear to be true. So the thing is, what they've done with the heliocentric model is just taken time. Those records of when and where we see the sun or the moon or the stars at any given time or any given location have been recorded and tabulated for millennia. You do not need to make any assumptions whatsoever about the shape or dimensions or apparent rotation or spin or speed or position of the Earth in order to make predictions, because it is no different than predicting how long it will take for something to occur on a clock. Okay, we can see from this in 10 minutes it's going to be 6:30. Yeah, we're just telling the time. Okay, and so this is the only prediction that you can make. You tell the time. It doesn't dictate or predict the size or the distance of anything in the heliocentric model. Okay, you understand, right? You understand that the globe is just a concept. It is just an illustration of time, and time is abstract. It's not based on any tangible measurements. It's based on converting intangible observations into an imaginary curve, using the geometry of perspective to create a dome of perspective across a level Earth. All right? So we understand that now, that there is a big difference between a measurement and a calculation. All right? We can make a physical measurement of this car. Okay? Now we could calculate that it's going to go a certain distance at a certain speed, okay? But again, that's all going to be relative to scale. How quickly does this car pass across your horizon if it's very close? How quickly does it pass across your horizon if it's very far? This all makes a difference, but you can't really know for sure unless you're actually measuring something tangible how fast this car is going, or the true distance of it, because you don't know the actual size. Yeah, up here, you could just, it's just big. All right, further away, this simple fact of life should be enough to help anyone who is defending their belief in the heliocentric model understand that it is in fact just a belief. It's not science. Being able to make predictions doesn't prove anything, but it has been used as indirect evidence to make you believe that you live on the outside of a spinning ball going around the sun. Okay? So nothing changes about what we see. When it comes to flat Earth, it is how we see it. It is level. It seems to be stationary. You can argue about the forces of gravity and things like that. But what we do see is the sun and the moon and the stars appearing to get further away from us from any given location, and we know that those distances are affected by perspective. But perspective is ignored and converted into an imaginary curve on the Earth. All right, I hope that makes sense. Thank you very much.